Hello, Chem 212 students, and welcome to Chapter 4, Alkanes and Cycloalkanes. In this chapter, we're going to learn all about what are otherwise known as hydrocarbons, and those with only single bonds. And so in the previous chapter, in Chapter 2, you learned about the functional groups and their names. Alkanes being the name for molecules with only carbon-carbon single bonds, and then there were alkenes, which had carbon-carbon double bonds, and alkynes, which had carbon-carbon triple bonds. We're going to be focusing just on alkanes in this chapter, and we use alkanes, hydrocarbons in general, for a variety of purposes. Smaller alkanes like propane, C3H8, these ones have weak van der Waals or London dispersion forces, as they're also called, and so they do not attract each other very much. They tend to be in the gaseous form. If you have 8-ish or so carbons, you've got a molecule with a little bit more London dispersion forces, so these can attract each other a little bit more strongly. This is like your gasoline. Gasoline is a real mixture of hydrocarbons, but it averages around 8 carbons. And then we have something like Vaseline, which is like these sizes, relative sizes of molecules here, about 20 carbons or more. And these come from the same place as the gasoline and the propane. They're from the fossil fuels, and they're cleaned up and then put in a nice jar so we can put this on our face to protect our skin and to keep the moisture in, because it's non-polar, so the water can't get through. So let's learn a little bit more about alkanes. Hydrocarbons in general are compounds that are composed of only hydrogen and carbon. And these include alkanes, alkenes like ethylene, or which is its common name or its systematic name ethene, acetylene, which is its common name or its systematic name that we will call it ethyne, and benzene. So these are all hydrocarbons, but we're going to be focusing on the alkanes. The alkanes have only single bonds, meaning they have the maximum number of hydrogens attached, and so we say that this molecule is saturated. One other thing to note is an idea called degree of unsaturation, or DOUs. So DOUs is a way to count, for example, either rings or double bonds. So a saturated hydrocarbon has a degree of unsaturation of 0. It has no double bonds, no triple bonds, no rings. It has every carbon is making a bond to the maximum number of hydrogens, so we call it saturated. Ethylene has a degree of unsaturation of 1. This is due to the double bond. So what a degree of unsaturation of 1 means is that you're going to have 2 less hydrogens that can attach, and you can see the result in the formula here. There's 2 less hydrogens. A triple bond confers 2 degrees of unsaturation. Therefore, you have 4 less hydrogens than you could have with the saturated compound with all single bonds. And so you get C2H2. Finally, benzene has 3 double bonds. Each one contributes 1 degree of unsaturation, and a ring. So that confers 4 degrees of unsaturation. 4. 1 for the ring, and 1 for each of the double bonds. Now you can see generally the formula for these is CN for a saturated hydrocarbon, H 2N plus 2. So if you had a saturated C6 hydrocarbon, the saturated would have 6 carbons, and it would have 2N plus 2, so 2 times 6 plus 2, 14 hydrogens. However, it is missing benzene is missing relative to the saturated hydrocarbon 8 hydrogens, 2 for each degree of unsaturation. So 1 DOU equals 2 less hydrogens compared to compared to CnH 2N plus 2, which is a saturated hydrocarbon with no rings. Saturated hydrocarbons are alkanes, do not have any pi bonds. They're only carbon-carbon single bonds. And we want to name these molecules such that if we have a name, it directly tells us the molecule. And if we have the molecule, there's only one name that can be attached to it. In other words, we want the names to be one-to-one with the structures. One structure, one name. If the name differs, it's a different structure. It's a different molecule. If the structure differs, the name should be different. And there's a systematic way of naming alkanes and other molecules that make sure that this is the case. For saturated hydrocarbons, we're going to name these molecules such that their name ends with ane. And you can see here we've got propane, which has 3 carbons, 1, 2, 3. We've got butane here, which has 4, 1, 2, 3, 4. We have pentane that has 5 carbons, 1, 2, 3, 4, 5. But they all end with ane because they're all hydrocarbons with no pi bonds, no double bonds, no triple bonds. Now, many compounds are known very well by their common names, and sometimes the common name is even accepted as being equally valid as the systematic name. However, in this class, we want to emphasize that we can tell the structures from the name. So in general, we are not going to be using common names. We're going to be using the systematic names. And so you can see here, this would otherwise be known as methanoic acid by its systematic name, but people very commonly call it formic acid. This comes from Latin. Urea, a compound isolated from urine. This is the way our body expels excess nitrogen from eating proteins, which contain nitrogen, as you'll find out in Chem 213. Again, this would have a different systematic name, but its common name is urea, and everyone really calls it that. Morphine, which is a painkiller in the opioid family, and barbituric acid. Again, these are common names, so they're still frequently used just because of history. But the preferred nomenclature is systematic, because again, these names don't tell us anything about the actual structures. If you don't have the structure memorized, you can't get the structure directly from the name. But the advantage of the systematic naming is that we will be able to determine the structure directly from the name and the name directly from the structure by using a system. And so in 1892, around the time organic chemistry was really blowing up and many compounds were being discovered, there was needed a systematic naming system so that we can name any molecule even if it had never been observed before. And so the IUPAC system was born, the International Union of Pure and Applied Chemistry. They're responsible for deciding mainly nomenclature and also things like updating the information that is relevant to the most modern periodic tables, among other duties. But their primary mandate is for naming. That's what they do. So we're going to learn the IUPAC system because we can't reasonably memorize a bunch of common names. It's not something we really want to do. So here's we're going to go through step by step how you apply the so-called IUPAC systematic naming system. So first of all, when you have a molecular structure, you're going to base the name off of the longest parent chain. And so that's the longest chain you can draw without picking up your pencil. So for example, the longest chain would not be this one, 1, 2, 3, 4, 5. We can do better than that. We can go longer than that. So you have to kind of guess and check a little bit and find the longest structure. In fact, the longest structure is this one shown here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. And so that's the longest pathway through this molecule. And so this will be the main carbon chain. Now, usually when people draw these, they draw the longest carbon chain left to right because it's easier to see where the longest chain is. However, that will not always be the case. So you always have to go through and check the longest chain. Finally, use table 4.1 to look up a prefix. Really, you should memorize some of these prefixes. So these prefixes tell you how many carbons are in the longest carbon chain or in the parent chain. This one has 9 carbon atoms. So here are these prefixes. I'm going to require you to memorize the names for chains 1 through 10 carbons in length, so up to decane. The hardest ones to memorize, the hardest prefixes, are meth, eth, prop, and bute, because these don't correspond to anything you might have seen before, really. They're unique to this naming system, or they're at least not commonly used. You may not have seen these prefixes before. However, these other prefixes, you've probably seen them before. Pent, they're the same prefixes that are used for geometric shapes. So a geometric shape that is 5-sided is called a pentagon. And the prefix for a parent chain having 5 carbons is pent. And a 6-sided polygon is called a hexagon. And so same thing. So hex for 6, hep for 7, octagon, you guys probably know the octagon if you watch MMA, non for 9, and dec for 10. So these you must memorize to do the naming, and you will memorize it probably just through the course of naming them. These ones we're not going to see as often, and I'm not going to put any with this big of a carbon chain on your exam. So it does go further in table 4.1, but this is good enough, up to 10. So if the parent chain has 9 carbons, the parent name is going to be non for 9 carbons, and ane because it's an alkane with only carbon-carbon single bonds. What if there is more than one possible parent chain? So here we have a parent chain with 1, 2, 3, 4, 5, 6, 7 carbons. But here there's another way we could draw this. 1, 2, 3, 4, 5, 6, 7. That way also has 7 carbons. So if there are 2 possible longest chains, your parent chain will be the one with the fewest, the most rather, not the fewest, the most substituents, not the fewest. So here, the correct 7 carbon chain would be 1, 2, 3, 4, 5, 6, 7, the one on the left, because that has 3 branches off the main chain. However, this one only has 2. So we would choose the structure on the left, or the naming. We would choose this as the parent chain, this 7 carbon chain. Also possible are rings of carbons, such as cyclopropane, cyclobutane, cyclopentane. So again, prop. So the cyclo here means that the carbons are bonded in a ring. The prop means that ring contains 3 carbons, and the ane means that the carbons only have single bonds between them, no double or triple bonds. Okay, same thing here. Cyclo is a ring. Carbons are bonded till they bond all the way back on themselves there. And bute means 4 carbons, ane means only single bonds, and same thing here. Cyclo, ring, pent, 5 carbons, 1, 2, 3, 4, 5, ane, or only single bonds. Okay, so let's find the parent chain. So the parent, again, finding the parent chain is just the first step. We're still on the first step, but we're practicing the first step here. So to find the longest parent chain, well, here we would have okay, here we would have 1, 2, 3, 4, 5, 6, 7, 8, and we could have just as easily gone the up way. As you'll see when we begin to name them, the naming will be equivalent if we go either way. Each of these 2 ways is the same. So this one contains 1, 2, 3, 4, 5, 6, 7, 8 for its longest chain. So we would use, for the parent chain, we use the prefix oct. And then since there's only single bonds, we would use the suffix ane, octane. Okay. And there's more to the naming. We haven't named any of the branches yet. So there are these branches here. There's a branch here, there's a branch here, there's a branch here. We haven't named those yet, but those are going to have to be a part of the name as well. All right. So let's now find the longest chain in this one here. So notice that the longest chain may be a ring. Okay. And so if the longest chain is the ring, so these are branches. These branches are smaller than the ring itself. So our parent chain in this case is actually going to be the ring itself. So since this has 1, 2, 3, 4, 5, 6, 7 carbons in it, this is going to be cyclo because it's a ring, and then hept because there's 7 carbons, and ane because there's only single bonds. Note that the parent name cannot include carbons that are inside a ring and outside a ring. So what you're doing is you're comparing the number of carbons in the ring to the number of carbons in the longest chain outside the ring. And we'll have a few more examples of that. But the longest chain here is the ring, 7 carbons. This branch here only has 1, 2, 3, 4. So this is a branch with 4 carbons. This is a branch with 2 carbons. This is a branch with 2 carbons. So all of those are less than 7. Okay. So now that we've named the parent chain, and again, as I was saying, usually the parent chain is written, crossways when someone's drawing a structure, because it's just easier to see where the longest chain is. Remember, going back a few slides here for these ones, it was hard to see where the longest chain was because the longest chain wasn't written left to right. But here it is. So it's really easy to spot the longest chain. The longest chain here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this name is going to end with dec for 10 and ane for all single bonds. Now, what about the substituents or the branches? So these are named in the same way or using the same prefixes as in table 4.1. However, their names will end with YL, which indicates a branch. And so the parent is called decane, and then this substituent here, which contains 1 carbon, would be called meth for 1 carbon, and il meaning branch, methyl. This branch here contains 3 carbons rather. Let's do this one here. It contains 2 carbons, 1, 2, and so its prefix would be eth for 2 carbons, and then il for saying that it's a branch or a substituent. And then this substituent contains 3 carbons, so we call it prop, and then il. So we've got 3 different substituents. And to name the entire molecule, we're going to have to put these together in a particular way. And so we'll get to that in just a moment. Let's keep going. So identify the substituents. So note that a ring here can be either the parent chain or it could be a substituent depending on how big it is. So for example, here the substituent contains 3 carbons and the ring contains 6. 1, 2, 3, 4, 5, 6. So the ring is the parent. And so we're going to call the cyclohexane. And then propyl will be a branch. And as we're going to see, we're going to write the names of the branches as substituents in front of the name of the parent. However, in this example on the right, the substituent only contains 3 carbons. So the parent here will be the branch off the ring called with 4 carbons. So the parent is going to be butane. But for 4 carbons, ane because they're only single bonds. And the branch is going to be the cyclopropyl. So we'll say cyclo because it's a ring, prop because the ring contains 3 carbons, and YL because it's a branch. And then this one here is what's known as a locant. And so as we start to put all the names of the parent and the substituent together into one name for the molecule, we're going to use locants to indicate where on the parent chain is a particular substituent. So here, let's name the substituents. So we had already found the longest chain here. The longest chain for this one was this one. And so our branches were right here, here, and here. So this is a methyl branch right here. And so is this one. 1 carbon. Meth for 1 carbon, YL for branch. This is an ethyl branch. Eth for 2 carbons, right here, 1, 2. And il for branch. Okay. And then here we have these branches. These two both contain 2 carbons, so they'll have a prefix of eth, and YL meaning branch. So the 2 carbons are right here, 1, 2. This branch contains 1, 2, 3, 4 carbons. So it will be called bute for 4 carbons, bute, and then YL, butyl, or branch. So that's how you name the substituents. Now, some of these substituents, they are quite complicated. So they essentially have their own substituents. And so that gets complex. This contains 5 carbons, 1, 2, 3, 4, 5. But we can't just call it pentyl. Pentyl would be if instead this wasn't branched, but it just kept on going. This would be pentyl. 1, 2, 3, 4, 5. However, in this case, there's a branch off of the main chain. And so calling it there's a branch off of the branch, essentially. A substituent on the substituent. So it doesn't make sense to call this pentyl because it's not. It's not the same as what pentyl would be. Instead, it's got a carbon branching off the middle, not going all the way to the end. And so we're going to have some special names for some of these branch substituents. And for the ones that we don't have special names, we'll have a special way of naming them. So, for substituents with complex branches, so a branch with a branch. So we look at the branch and we find the longest chain within that branch that's connected to the main parent chain. That would be this one right here containing 4 carbons. 1, 2, 3, 4. Okay. And then we find where the branch is. So in our branch, our main branch, we have 4 carbons. And then there's a branch off the branch right here, which contains 1. So we name first we write at the end, we would write the name of the parent chain on the branch, which would be bute, would be the prefix for 4 carbons, and it would be YL because it's a branch. But then before that, we're going to put the name of the branch, which contains 1 carbon, so it would be methyl. And then finally, we'll use a locant to describe where the branch is. It's on the 2nd carbon from where the branch begins. So we would call this 2, and we always put a dash between numbers and letters. So make sure whenever you're writing the name, numbers and letters are never touching. There's always a dash between the numbers and the letters. So this substituent would be called 2-methylbutyl. And then to complete the name, we've got a very long parent chain right here, which contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 carbons in it. So it'd be undecane at the end. Now, there's some branches, okay, some complex branches that are so common that they have their own special names. So if you have a parent chain here with 3 carbons attached in a line, 1, 2, 3, that's called propyl. But if the parent is attached to the middle, so notice here the parent's attached to the end of the carbon, the last carbon. Whereas in this one, it's attached in the middle right here. And so you've got 3 carbons still, 1, 2, 3. However, there's essentially a branch. So we would call this ethyl being the main chain here. So if the main chain is ethyl, 1, 2 carbons, the branch would be this here. So we would call it methyl ethyl, specifically 1 methyl ethyl, because the methyl branches. But no one really ever calls it that. They call this isopropyl. And so isopropyl is going to be the preferred way to name this. And so that's going to be, unfortunately, a name that you will have to memorize. There is a few memorization things that are going on in this chapter. I know I try to minimize memorization, I always told you, but when it comes to names, it's like there's no way around it. You have to memorize someone's name, and you got to memorize a molecule's name. Now, this system does reduce the memorization significantly, but there are a few things you need to memorize. You need to memorize those prefixes, and you need to memorize what isopropyl is. And there's a few more that you should memorize. You need to memorize these. These are the ones associated with butyl. So a butyl branch would contain 4 carbons in a row, like we see on the left here, 1, 2, 3, 4. However, it's possible that it could branch in different ways. And so here, instead of the parent being attached to the carbon on the end, here it's attached to the first carbon. And so in terms of the naming, as a branched branch, a substituent with its own branches, the main chain of the branch would contain 3 carbons, prop, and it's a branch, so propyl, and then it would have its own branch with 1 carbon, methyl, and that branches off the first carbon from the parent, so 1-methylpropyl. But again, people don't usually call it that. They call it sec-butyl, and so you have to have this memorized. The sec means that it's attached to the second carbon. It actually means it's secondary, which means it's attached to a carbon that's attached to 2 other carbons. So we call this sec-butyl. I just remember it because it's on the second carbon, so sec-butyl. There's also isobutyl. So here we have the main chain is also, again, contains 3 carbons, and then there's a branch right here. And so we have 2-methylpropyl, 1, 2, 3, propyl. So the propyl comes from the fact that the main branch has 3 carbons, and then it has a branch itself with 1 carbon, and that's on the second carbon away from the one attached to the parent. So this would be the first one, this will be the second one. But no one calls it that. Everyone calls it isobutyl. And the ones that are iso tend to have branches that are not off the main carbon, the ones that are called iso. So that's just some general way, so you don't have to memorize 100%. This is just when they're saying iso, it's generally one where there's a branch on the, branching off on the carbon next to the carbon attached to the parent. Finally, there's tert-butyl, and so here we have the main chain here. We could choose any of them, having 2 carbons, and they have 2 branches. So this would be called dimethyl ethyl. So ethyl being the main chain with 2 carbons and then 2 methyls, and 1,1 because both methyls are attached to the first carbon. However, everyone calls this tert-butyl. And the tert stands for tertiary, which means that the carbon attached to the chain, the parent chain, is attached to 3 other carbons. So secondary here, attached to 2 carbons, tertiary attached to 3. And so that's ways that you can memorize these without fully memorizing if you understand why they have these sec, iso, tert. But that's going to conclude all the ones that I want you to memorize. You must memorize these. So you must memorize isopropyl. You must memorize isobutyl. So you see that kind of pattern between isopropyl. Here it's branching from the first carbon because that's all there is. And then here it's branching like this here. So you see that pattern of where iso comes from. Now, the ones for 5 carbons, You don't need to memorize these. You may want to, but I won't require that you memorize them. So here we have, if you have a parent, it looks like isobutyl and isopropyl, except now the branch is 2 away, right? And so you have that same iso shape with these 2 branches sticking out, isopentyl. And then there's neopentyl, where off the second carbon you've got 2 branches. You do not need to memorize these. So you may want to memorize these. These you have to memorize. So this one you have to memorize. Okay. This one you will need to memorize. This one. But the ones with 5 carbons you may want to, but you don't have to. Finally, to put the substituent names and the main parent names together, we need to indicate where the branches occur, on what part of the molecule. And for that, we use what's known as a locant. And so we assign numbers to the carbons on the main chain. And we assign them in such a way that we start on the end that is closest to the first branch. So here we would number it like this: 1, 2, 3, 4, 5. And we would not start from the right, 1, 2, 3, 4, 5. The reason why we start from the left is because we want that branch to be on the second carbon, not on the fourth. We want the number indicating the branch to be as low as possible. And so here we can see we number it 1, 2, 3. So these are both methylpentane. Okay, the ane means these only have single bonds. The pent here, pentane, means that the parent chain has 5 carbons in it. Methyl means the branch has 1 carbon right up here. 2 means that the branch is on the second carbon right here. Whereas with 3-methylpentane, it's all the same except there's a 3 at the front, and that's because the methyl branch here comes off the third carbon. So these are isomers of one another. They're both C6H14. I encourage you to count the hydrogens for practice. You may want to pause this and count the hydrogens. But this has the branch on the second carbon, the methyl branch. This one has the branch on the third. So another important point is that the fact that these names are different tells you they're not the same molecule. Isomers of one another do not have the same name because they have different structures. They will have different names. If you name 2 molecules, or what you think are 2 molecules, and the name comes out exactly the same, those are not isomers of one another or different molecules. Those are exactly the same molecule. The names are 1-to-1 with the formulas. When you're assigning the locants, again, always be sure to start from the end closest to the first branch. So, for example, 1, 2, 3, 4, 5, 6, 7, not 1, 2, 3, 4, 5, 6, 7. There's no such thing. Let's name this too. So, and you may want to pause the video and try to name it yourself. The main chain has 7 carbons, so its prefix will be hept, and there's only single bonds in this hydrocarbon, so the suffix will be ane. There is a branch here with 1 carbon, so meth indicates 1 carbon and YL indicates branch, and that branch occurs on the second carbon, so it's 2-methylheptane. There is no such thing as 6-methylheptane, because even if this branch were over here, that's exactly the same molecule. You just take it and you flip it around like a pancake, and it's exactly the same. So that's where naming is really useful for helping you to determine whether you have an isomer or a different molecule or exactly the same molecule. If you can't tell because of the way they're drawn, because they're drawn funny, name the molecule. If the name comes out the same, then you have exactly the same molecule, as long as you followed the naming rules. If you name this 6-methylheptane, clearly that would look different, but it's because you named it wrong. So be careful about how you assign the locants. Okay, when you have more than one substituent present, you have to number the chain such that you give the first substituent the lowest number possible. So here you can see that there are two branches closer to the right. However, if we number from the right 1, 2, 3, we get to these branches at number 3. However, if we number from left to right, like on the left, 1, 2, we hit the first branch at number 2. And so our branches are going to be at number 2 and 2 branches at number 5. And it's because the 2 beats the 3. If you have a tie with the first number, you move to the second number. Decide which direction to number from. So here's an example where you have a tie for the first number. If we number from right to left, 1, 2, 3, 4, 5, 6, 7, we hit the first branch at carbon number 2, and we hit the second branch at carbon number 3. And the third branch is at carbon number 6. If we number left to right, 1, 2, 3, 4, 5, 6, 7, we hit the first branch at number 2 as well. So the 2 was a tie. So we need to go to the number of the next branch for the tiebreaker. On the left way of assigning the locants, 3 is the locant for the second branch. Whereas if we number from left to right, 5 is the number for the closest second branch. So we would number it as we see on the left, from right to left, not the one on the right. Okay, if there is no tiebreaker, then you're going to, if you go all the way down the line and everything's the same, like here, it's going to be 1 and 5 or 1 and 5. 1 for the bromine, or 5 for the chlorine, or 1 for the chlorine, 5 for the bromine. If there's no tiebreaker, then finally you decide based on the name of the substituent. And so for halogens, what you're going to see here is for halides, their substituent names end with O. So we don't call this bromine as a substituent. Now we call it bromo. We don't call this chlorine, we call it chloro. And then there's also for iodine, iodo. So for iodine, it would be iodo. And for fluorine, it would be fluoro. And because B comes before C in the alphabet, and we can't, and we only do this when we can't break the tie with numbers, then we finally go to alphabet. So since B comes before C, we're going to make bromo number 1, and we're going to make chloro number 5 instead of the opposite. These same rules apply for cycloalkanes. The only difference with cycloalkanes is that when you number, you can start with number 1 anywhere on the chain. So you're going to want to choose the part of the chain where it has a branch. You're always going to start numbering from a branch. And so here we're going to number from the branches on the left, because if we list all of our branches, we have 2 on number 1. So we'd say 1 and 1. This branch is 1. This branch is on carbon number 1. And this branch here, this methyl branch, is on carbon number 3. But we number this 1, 2, 3, not 1, 2, 3, not like on the right, because then the second branch would be at the third. So the rules apply the same with cycloalkanes. The only difference is you can put number 1 anywhere on the ring. So you put it where there's a branch. Finally, when we're assembling the complete name, we assign a locant to each substituent, and we write them in the name before the parent chain in alphabetical order of the substituents. Note that any prefixes used do not change this alphabetical order. It's in terms of the name of the substituent. For example, ethyl is written in the name before methyl, because E comes before M. And it doesn't matter if there's di or tri. If we have more of these, we'll use di or tri or tetra or penta. The prefixes do also prefixes like iso and tert butyl, and so are not used except for the prefix iso. Okay, so the I in iso counts, but the tert in tert-butyl, it does not count in terms of the alphabetical order. So only iso is the only one that counts. So now let's name this cycloalkane using what we know. We're going to number 1 here because that's the closest branch. We've got 3 methyls. So our main chain is going to be the ring. And so we're going to say cyclo, because it's a ring, hex, because that ring contains 6 carbons, 1, 2, 3, 4, 5, 6, and then ane, because there are only single bonds in that ring. Now we have 3 methyls. So we don't just say methyl. Here we use a prefix like di, tri, and this is supposed to say tetra, sorry. It says terta, and it's supposed to say tetra, not terta. Tetra, penta. And so here we've got 3 methyls. 1 here, 1 here, and 1 here. So since we have 3 of the same group, we're not just going to say methyl. So meth meaning 1 carbon on the branch, YL meaning branch. We're going to say trimethyl because we have 3 of the methyls. And finally, we're going to place our locants. So we always separate the numbers and the letters with a dash. And then we write down the locant numbers. 1 for this first branch. Then there's a second branch on 1. So we put a comma and we write 1. And then finally, there's a branch here on the 3rd carbon. So we say 3. And we always separate the numbers and the letters with a dash and the numbers from one another with commas. 1, 1, 3, trimethyl cyclohexane. So here's the summary of how to name alkanes. Number 1, identify the Paris chain, which is the longest chain of carbons that you can draw on without picking up your pencil. Then identify the substituents and name them. Then number the parent chain and assign a locus. Give the first substituent the lowest number possible. If it's tied, go to the second substituent. If it's tied, go to the next substituent. If all the substituents are tied in terms of numbers, then you use alphabetical order as a tiebreaker. Finally, you list the substituents before the parent name in alphabetical order. And prefixes do not impact this alphabetical order except for iso. Okay, so let's take a look at a couple more examples here. So our first job on the top here, we're going to name this, is to find the longest carbon chain, the parent chain. And so it's looking like it's going to start. Now we can start either right here or right here. Notice that they both have 2 carbons. So in terms of visual appeal, I think it's good to start here. 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we could either go up or right here. It's the same. Because if we go here, this will be carbon 9. This will be a methyl branch. If we go down here, this is carbon 9. This is a methyl branch. It won't impact the naming. So that is our main chain. And then we're going to have a 2 carbon branch right here, a 2 carbon branch right here, and a 3 carbon branch here. Now this one is got 2 carbons in a line, so it's called F for 2 carbons and YL for a branch. This branch contains 1 carbon, so it's called meth, and then it ends with YL for branch. And this branch has its own special name. It's called isopropyl. You probably heard of isopropyl alcohol before. Isopropyl. What isopropyl alcohol is it's isopropyl but attaches an OH instead. And then for the name chain, the name contains, or the chain contains 1, 2, 3, 4, 5, 6, 7, 8, 9. And so the main chain will be called non for 9, ane for only single bonds. Okay, now we want to assign locants. And oops, we have one more branch too that I missed. This branch right here. It's a methyl. Okay, so if we assign the numbers, if we go 1, 2, 3, 4, 5, we get to the first branch at carbon number 2, but we don't get to the next branch until carbon number 5. So it will be preferable to number in this fashion from here, 1, 2. Oh, actually no. If you notice, we get we don't get to the first branch until carbon number 3 here. So actually that would be incorrect, because if we go the other way like this, 1, 2, we get to the first branch at carbon number 2. And so we're going to number from the right side to the left side. So there's going to be 3, 4, 5, 6, 7, 8, 9, like that. And so in terms of writing the name now, we're going to end the name with non-ane. That's the parent. Okay. And now we're going to alphabetize these. So the I does count in isopropyl. And so it's going to be the ethyl that comes first, the methyl that comes last, and the isopropyl that comes in the middle, because I comes before M. So we're going to write the methyls right before the non-ane, and there's 2 of them. So we're going to say dimethyl. So di indicating 2 of the same group. Next, we're going to put the locants. We always separate the locants from the words with a dash, and the locants are going to be 2 and 6. We're going to say 2, 6, and then we're going to put another dash. So 2 for this methyl branch, 6 for this methyl branch. Then before that, ethyl will come before isopropyl, so we're going to do isopropyl. So we'll say isopropyl. And then again, notice as a dash, we never let the numbers touch the letters. We're going to put another dash. The isopropyl is on carbon number 5. And so we're going to say 5 isopropyl. Finally, we've got an ethyl on carbon number 7. So we're going to say 7 ethyl. 7 ethyl, 5 isopropyl, 2,6 dimethyl nonane. Okay, and so that's going from the formula to the name. Now for this next one, you might want to try it yourself before I show you the answer. Go ahead and pause it. Again, whenever you want to try one of these questions on your own, just pause it. If you think you got it, give it a shot. Just pause the video, give it a shot. You can do it, you know. Okay, so we got cyclohexane. So cyclohexane. So we always start here with the parent chain. So it's cyclohexane. And so that's going to have 6 carbons in a hexagon shape. And then I can number my carbons however I want because it's a ring. So I'm just going to call the top, I'm going to number them like this. I'm going to say 1, 2, 3, 4, 5, 6. Okay. So on the 4th carbon is a methyl. So I'm going to draw the methyl downward like that. 1 carbon here. On the 2nd carbon is an ethyl. So eth means 2 carbons. So on the 2nd carbon, 1, 2, 2 carbons right here, 1, 2. And then on the 3rd carbon is a cyclopentyl. So this is the 3rd carbon here. Now cyclopent, that is that contains 5 carbons, pent, in a ring. So there it is. And then finally 1 tert-butyl. So tert-butyl means that it contains 4 carbons altogether. It's tertiary, meaning that This carbon here is attached to 3 carbons, but altogether it contains 4. 1, 2, 3, 4. So notice that the butyl here, butyl came first because the tert doesn't contribute to the alphabetization, and so B comes first. The C here does contribute to the alphabetization. It's a part of the name of the substituent. So C here comes after B. Then E comes next, ethyl, and methyl comes last. So that's all alphabetical. Okay. So that's how you do the naming of these hydrocarbons. In terms of bicyclic compounds. So you're going to see a few of these. You've probably never seen these before this class. They've got 2 fused rings. So we've got a ring here, essentially, and a ring here. And they're joined at the top. And there's multiple ways to draw these. They're kind of hard to draw in 2 dimensions because they're very 3-dimensional shapes. So there's a few different ways that they can be drawn. So if we look, let's see here. Let's take a look at these 2. So notice that these 2 cyclic compounds are not exactly the same compound. They each have a big ring here that contains 6. 1, 2, 3, 4, 5, 6. And then the point right here. So 7 total carbons. However, notice that on this side, there are 2 carbons that go between the bridge here. The bridge, they call this the bridge head, the bridge. Whereas here, there's only 1. And so these are 2 different compounds, and they must have the same name, okay? And this is how the names work. The names are based upon how many carbons are in each of the sections of the ring. So we call both of these heptane at the end because together they all have 7 carbons. 1, 2, 3, 4, 5, 6, and then 7 at the top. 1, 2, 3, 4, 5, 6, and then 7 at the top. So they both end with heptane, and they both begin with bicyclo. Bicyclo meaning 2 rings together. However, this one's called 3,1,1 heptane. 3 being the longest area without the bridgehead here. 1, 2, 3. That's where the 3 comes from. Then we put a dot. 1 for this 1 carbon between these 2 points here. And finally 1 for this carbon up here. Whereas here, this is bicyclo 2,2,1 heptane, because on this side there's 2 carbons here. On this side there's 2 carbons, and there's 1 carbon here between the 2 sides of the ring here. And so that's how you differentiate between 2 bicyclo compounds. That these are isomers, but they're just joined in a different place, so they're different molecules. When you're numbering, when you have substituents and you're numbering a bicyclo parent chain, start at a bridgehead carbon atom. This is either the one called 1 or 5 here. So the bridgeheads here, you can tell they have 3 carbons attached. And this is where the 2 rings are joined. And then you number around the side with the largest number of carbon connectors first. So we're going to number around the right side here because it has 3 carbons in between rather than 2. Okay. Finally, while following this rule, we want to number around in a direction that will give our substituent the lowest number. And so, for example, with this one here, we would make this one number 1 and go 1, 2, 3, 4, 5 because we're numbering around the longest region here, the longest number of carbon chain connectors, and then we get to the branch at number 6. Whereas if we number around the other way, we get to the methyl branch at number 7. And so in terms of assigning locants, you'll want to do this in such a way that you end up at the branch with the getting to the lowest number first. Okay. Finally, in terms of when we get to large molecules, okay, the systematic names become increasingly complex the larger the molecule is. And so this is why for many drug molecules and the common name is given. So when you go to the pharmacist to get a medicine or something, the name generally isn't written as you see here, all long and drawn out like this. A shorthand common name is given. Although the strength of the IUPAC system is that it has rules that allow for the systematic naming of any compound, whereas common names they're just a name that's just made up by someone. They have nothing to do with the structure. So the molecule up above is called Nexium. It's a drug for acid reflux, and that's why people call it Nexium, because this is a whole mouthful. However, if you really wanted to know the structure, which generally we do when we're doing organic chemistry, it's valuable to have the systematic name. Okay, and that's going to end the part of the chapter about naming alkanes. When we return, we'll continue by talking about isomers and the way in which carbon atoms and bonds and stuff can spin around and move around, various conformations, as they call it, of molecules. So I'll see you in the next video.